Hey. Yeah, so far we've been through 7.2 and 7.3 problems. Now today I'm going to try to get to 7.4 and 7.5 problems, just do a couple out of each section, just give you an idea of how things go, or at least what I'm thinking when I'm doing the problems. Yeah, so and then that'll be the wrap-up until exam 3, and if any of my students have any more questions, just go ahead and ask it on Canvas. Remember, don't comment on these videos. And if you're a bystander out there watching these videos and you have some questions, yeah, please free to ask down in the comments. But again, if you're my students, do it on Canvas. Let's see, so 7.4 was all about the inverse Laplace transform. And that means that we're going to be using a lot of partial fraction decompositions, and then using the linearity property and then the tables to match up and invert. And then after that, we have the 7.5 section where we have a bunch of problems related to actually solving initial value problems, the whole point to this whole Laplace transform section. And so there I'll show you some examples. I'll do one or two with constant coefficients and then see if the book has a good problem for non-constant coefficients, just like that last example I posted. As far as my students are concerned with the exam, because it takes so much time to do things with the non-constant coefficients, because that just sets up a whole other differential equation, what I'd be looking for there is just to make sure that you can accurately transform it from one differential equation to another for the non-constant coefficients. And for the constant coefficients, that's really just going to be, again, just like the inverse Laplace transform, where you do partial fraction decomposition and all that good stuff. So just so you have an idea of what's going on there. For the inverse Laplace transform, I mean, really doing 7.5 is just going to be doing all of that over again. So on the exam, I mean, I might have a couple places where I ask you to find the inverse Laplace transform, but the bulk of that work is really going to be found in the problems coming from section 7.5. Okay, so let's see, what else? Yeah, so we're coming up to exam 3, and then after that it's going to be the final. And then, what else do we have? So between the final and exam 3, I think I'm going to throw in the convolution section, and then we'll do a special topics video if we have time. If not, I mean, I'm continuing this channel, so I mean, tune in later and I'll throw stuff up on fractional differential equations and also control theory and tidbits here and there. And yeah, I think that's good. Anyway, yeah, on a completely non-mathy note, if you've been looking out there, we've had a full moon recently, and I managed to get a couple of good shots of it. At least I thought so. We'll see in the footage in a second. And yeah, just not getting outside a lot. So that was probably the most outdoor experience I had in the past month. Almost always entirely constrained inside, either watching babies or working as much as I can. And I try to get a run on the treadmill here and there, but other than that, I'm just pretty much trapped. You know, I mean, that's this whole social distancing quarantine thing, so quarantine content, is that what YouTube people are calling this? Anyway, but yeah, so let's get down to it.
Okay, welcome back. Alright, so let's take a look at section 7.4, and so these problems out of Nagle, Saff, and Snider. And this is 9th edition. Alright, so this is section 7.4, and this is the inverse Laplace transform section. So let's take a look at a few of the problems here. So take a look at, say, 5, 7, and 9. Alright, well, let's just do 7 and 9, and then I can grab another more interesting problem later. So 7, 9, and 19. Okay, so number 7, if we take a look, it's 2s plus 16 divided by s squared plus 4s plus 13. Right? Yep, that's what they got. Okay, so now if we take a look at this problem, what's going on in the denominator makes a huge difference as to what we're going to do. as far as resolving the problem. So if we can actually factor the denominator into, say, two different factors, so something like this, R1 and R2, then we use partial fraction decomposition. However, if it ends up being something like s minus a squared plus b squared, then it should be some sort of shifted sine or cosine. And so we need to figure out if this is a reducible polynomial or if it's not. All right, so the way you do that is you try completing the square, or you just try to factor it. 13 doesn't have very many factors. You have like 1 and 13, and obviously neither of those is going to add up to 4. And so, so one thing you can do if you suspect that it should still be factorable is to just use a quadratic equation. I'm really guessing it's not. And so what that's going to leave us with is doing completing a square. So if we take s squared plus 4s, and then if I want to complete this square, then I need to add b over 2 squared. So I'm going to add 2 squared. So that's 4. I'm going to subtract 4, and then we still have 13. And so then ultimately what that gives us is s squared plus 4s plus 4 plus 9. Right? That's no coincidence. That's a perfect square. And so you have s plus 2 squared plus 9. Okay. So this is irreducible quadratic, and for the irreducible quadratics, that's going to turn us to looking at things like the sines and cosines. So for instance, if I take a Laplace transform of sine of bt, that's going to give us b over s squared plus b squared. And if I take a Laplace transform of, say, cosine of bt, then remember that gives us s over s squared plus b squared. Now, as far as shifting, well, if we put in the Laplace transform of e to the at times f of t, then that's going to give us the Laplace transform of f of s minus a. Okay, so so we have some sort of shift going on in here. We have a plus 2, so we're basically going to be looking for Laplace transform of these guys shifted by 2, right? So so ultimately that's what we're looking for, and so why don't we just go ahead and start with that. So we have 2s plus 16 divided by, it looks like s plus 2 squared plus 9. All right, what I have an s here and I have a 16 here, and if we have a constant, that should correspond to sine, and if we have a linear term, that should correspond to cosine. So I'm going to split this off into 2 pieces. And another thing I need to keep in mind is that I should have a s plus 2 up here, not just an s, because I need to match this shifting property. So let's be explicit then. So we have e to the minus 2s times cosine of bt then is going to give us, all right, let's not kid around, it's not b anymore. We see we have a perfect square there. Oops. Oh my goodness. All right, so it's not just b here, it's 3 squared. So 3t, this is one thing we're looking for. And so that's going to be s plus 2 divided by s plus 2 squared plus 9, right? And the other thing we're looking for is Laplace transform of e to the minus 2s sine of 3t. And this is going to be, say, 3 over s plus 2 squared plus 9, right? Those are 2 quantities we're trying to turn this into. And so there's going to be some scaling that's happening, and that's okay. Let's isolate our thoughts over here. And so what's going on? Well, one thing I can do to jump into this immediately is I can add and subtract 2 inside that s guy. So I'm going to say s plus 2 minus 2 plus 16 divided by s plus 2 squared plus 9, right? Then we can distribute this 2 to this piece and this piece. And what we're going to end up getting is we're going to have 2 times s plus 2 minus 4 from this guy times this guy. And And then we have plus 16, and so so I'm just going to say plus 12, right, over s plus 2 squared plus 9. All right, now I'm going to split the sum, and so that's going to give us 2 pieces here. It's going to give us 2 times s plus 2 divided by s plus 2 squared plus 9. All right, so this was our cosine piece. And now we're going to have another piece. Here we have plus 16, and, sorry, not 16 anymore. We have plus 12. And so it's going to be 12 up here. We have s plus 2 squared plus 9. But that 12 turns into 4 times 3, right? So instead of just writing 12, I'm just going to write 3 here. I'm going to put 4 here, right? And then that matches up exactly with our sine piece. So this ends up being cosine, like that. And this ends up being sine, like that, right? And so the inverse Laplace transform of 2s plus 16, trying to get away from this Laplace transform that we have, 13, is actually going to be 2 times e to the minus 2s cosine of 3t plus 4 times e to the minus 2s times sine of 3t, right? And that is the answer. Okay. So it's just a game that you're going to have to learn how to play. The whole goal is to work this into a form that we can just easily identify as corresponding to some Laplace transform bits. So what did we know? The first thing we did is when we saw this denominator, we went ahead and determined whether or not this denominator was reducible. If it is not reducible, that means we're talking about sines and cosines. And so I just reminded myself what those were. And also on the table, we actually have these forms too. And so when we see that we have s plus 2 here, we know that we're actually going to be talking about these exponentials times sines and cosines. Okay. And so, so then I said, all right, I need to change this guy into it's irreducible, like say, what do they call it? The point vertex form or something like that. I can never remember. It's been a long time since I taught pre-calculus. Anyway, so then we're left with a denominator here. I know I want to get s plus 2 out of this guy. And the best way to do that is to add and subtract 2. There's other ways you can do it. You can be clever about it. You can pull out a 4 out of this and try to factor it out, and that'd be fine. But I just find it faster just to add and subtract 2 and see what falls out. So then after I do that, I get this. And I split sum into 2 pieces, the one that has the s plus 2 piece and one that doesn't, has a constant piece. The one with the s plus 2 piece is the one that corresponds to cosine. The one that corresponds to the constant piece corresponds to sine. So that's what we got. And there we go. Okay, cool. So that's number 7. And let's go on to move to number 9. All right, take a look at number 9. We have 3s minus 15 divided by 2s squared minus 4s plus 10. Okay. So the goal is to go ahead and factor this the best we can. Let's see. I hate when we have something that's not monic. That makes it a little bit more difficult. One thing you could try is just factor out a 2. So you can say, take a look at 2s minus 2s plus 5, right? And now we'll see if that has any nice way of factoring. So again, what we're trying to do is we're trying to see if this is irreducible. If we can factor it, then we can split it using partial fraction decomposition. And if we can't, then we need to use the cosine and sine things. Because we have a minus 4 in here and the plus 10, it kind of gives me an idea that maybe this should be. Maybe. But we'll see in a second. So 5 breaks down into 1 and 5, and there's really no way that these can add or subtract up to -2. So maybe this guy is actually irreducible. Maybe. Let's see. Yes, I think it will be. Specifically because we know that s squared minus 2s plus 1 is how you complete square there, and that is going to have a vertex at, say, x equals 1, or s equals 1. And so now we're just shifting up by 5, so that's definitely not going to have a factoring. Okay, so now we just use our completing a square method, and so we're going to get 2, and so we have s squared minus 2s complete square, and then plus 5. So this is going to leave us with 2 times s minus 1 squared plus 4, right? And so that's what we end up having over here. So 3s minus 15 divided by 2 times s minus 1 squared plus 4. Okay, so now let's go ahead and see what we got. All right, so again, we have this form where we have an irreducible on the bottom, and that means that we have a Laplace transform, and it's shifted, so it's going to be a Laplace transform of, say, e to the t. The 1 times t up here is just coming from the fact that it's a minus 1 here that we're shifting, times, say, sine of, since we have a 4 here, I'm going to put it 2t, and so that's going to give us 2 over s minus 1 squared plus 4. And then the other one we're looking for is e to the t cosine of 2t is equal to s minus 1 over s minus 1 squared plus 4. Right? And so these come straight from the table. All right, so that's what we're looking for. We're trying to find these guys in this jungle here. All right, so let's go ahead and start doing it. So one thing we're going to do here, again, is I'm going to take the s, I'm going to add and subtract 1. Right? So this is equal to, say, 3 s minus 1 plus 1, what's that, s? And then we have this minus 15, and this divided by 2 s minus 1 squared plus 4. All right, I distribute the 3, so we get 3 times s minus 1 plus 3 minus 15 divided by 2 times s minus 1 squared plus 4. All right, now I get 3 times s minus 1 minus 12 divided by 2 times s minus 1 squared plus 4. All right, now I can split it up. So we know this s minus 1 bit with this should correspond to this whole cosine thing over here, and the constant one should correspond to the sine. So I'm going to have, say, 3 over 2 s minus 1 divided by s minus 1 squared plus 4. And now I'm going to have minus, so we had 12 divided by s minus 1 squared plus 4. I'm looking for a 2 up here. So I'm going to split this 12 into 6 and 2, and there we go. So now we have, oh, and don't forget, we still had 3 over 2 times this whole bit. So make that a little clearer. Say minus 3. That's not improving anything. 3 over 2. There we go. Maybe a little better. Okay. So then we have 3 halves of e to the t cosine of 2t. Oops. Let's be explicit about this. It isn't equal to that. What we have is the Laplace transform of this guy is equal to all this. So we have a Laplace transform inverse of 3s minus 15 divided by 2s squared minus 4s plus 10 is equal to 3 over 2 e to the t cosine of 2t minus 3 over 2 times 6, and so that's, say, 9 times e to the t sine of 2t, right? And there we go. That's the answer. Okay, so those were 2 problems with irreducible denominators. Let me see if I can find one that doesn't have an irreducible denominator. Let's just take number 6. All right, so if we take number 6, we have 3 divided by 2s plus 5 cubed. Okay, now let's figure out what this has to be. So something cubed here that makes me think of, say, Laplace transforms of t to the n. And so it's going to be n factorial over s to the n plus 1. So maybe I'm looking at something like the Laplace transform of t squared. But also remember, since we don't just have just s here, it's been shifted, right? So this is the Laplace transform of, say, e to the at times t to the n, and that's again going to be a shift. So it's going to be s minus a here to the n plus 1, right? And so that these come straight from the table, and so let's go ahead and take a look what we got. So I'm just trying to put this into a form where it's something like this, and so I'm going to have we're going to go ahead and factor out the 2. So it's going to be 3 divided by, say, 2 cubed, or 2 cubed, which is 8. S plus 5 over 2 cubed, all right? And so then we have, say, 3 over 8 times 1 over s plus 5 thirds cubed. Now we don't want a 1 up there anymore. We want 2 factorial if it's going to work out. So it's going to be 2 factorial, and then we divide by 2, and that 8 becomes 16. Okay, so now let's take a inverse Laplace transform of 3 over 2s plus 5 cubed. And what is that going to give me? Well, we know we have 3/16 coming out from here. We can pull that out of the inverse Laplace transform. And what's left here is this. And so this is going to be e to the minus whatever we have in there, so minus 5 thirds t, and then times t squared. And that is the inverse Laplace transform. Much easier than the last problem, so, and that's generally what we're going to be doing. Okay, cool. Now let's go on to the next problem. Let's take a look at number 19. So number 19, we have 1 over s minus 3 times s squared plus 2s plus 2. All right, now what we need to do is partial fraction decomposition. We definitely have this guy as 2 factors, right? And I think this one is irreducible. And in fact, if we take a look at it, it's s squared plus 2s plus 1 minus 1. And so then that's going to be s plus 1 squared plus 1. Yeah, that is irreducible. Let's move this over here so we get space. So we put that over there. Okay, and so I'm going to have to use partial fraction decomposition. So we're going to have a over s minus 3 plus bs plus c divided by this irreducible s plus 1 squared plus 1. All right, now it's a game of figuring out what a, b, and c are. After we do this, we'll talk about how to do the inversion for all this stuff, but right now we need to stay focused. So, figuring out what a, b, and c are, we're going to multiply both sides by this, and so what that gives us is that we have 1 is equal to a times s plus 1 squared plus 1, and then plus bs plus c times s minus 3. Now, if I want to figure out what a is, I can just go ahead and choose s is equal to 3, and that eliminates the entire second term with bs plus c, right? So what do we get? So we get 1 is equal to a, and then we have 3 plus 1 squared, that's 16, plus 1, so that's going to be 17, plus 0, and so that tells us that a is equal to 1 over 17. All right, now, if I choose something else, so let's say, so the thing is, this guy is never going to be eliminated unless I use complex numbers, and I don't want to do that. And so what I'm going to choose instead is I'm going to choose s equals 0. That's going to kill the b, and I can replace a with what its value is. And so, so then if I choose s equals 0, get 1 is equal to a times 0 plus 1 squared plus 1 plus 0 plus c times 0 minus 3. right? And so we know that a is actually 1/17, so we get 1 is equal to 1 over 17. And then we get times 2, it looks like, plus, or say minus 3c. All right, now I can go ahead and use that to figure out what c is. So we have 1 minus 2/17, so that is going to be 15 over 17. And it is equal to minus 3c, and so that tells us that c is equal to minus 5 over 17. Okay, so now we can just plug all this stuff in and figure out what b is, and we have to pick something to throw in for b. So I don't know, let's just pick s equals -1. Just doing that to make this guy go away. And so so we get 1, you can pick any s, honestly, at this point. So we get 1 is equal to a times 0 plus 1, and we get plus negative b plus c, and then we get minus 4, right? And if I go ahead and plug in what all these values are, I get 1 is equal to 1 over 17 plus negative b minus 5 over 17, and then times minus 4. So then 1 minus 1/17 is going to be 16 over 17. It's equal to 4b plus 20 over 17. And now if I subtract 20 over 17 over, I get minus, say, 4/17 is equal to 4b. And so then we get b is equal to minus 1/17. Okay, so what do we have now? So putting everything together, we have transformed our problem from being this to being this. So we have a is 1/17 over s minus a, or s minus 3, sorry, plus minus 1 over 17 s plus minus 5 over 17 divided by s plus 1 squared plus 1. All right, now let's take this to the next slide, and we'll figure out exactly what this is when we take the inverse Laplace transform. Okay. All right, so what we're trying to do is try and figure out what the inverse Laplace transform of this is, and let's clean this up a little bit. So I can actually factor out a 1 over 17 out of everything. That leaves me with 1 over s minus 3 plus negative s minus 5 over s plus 1 squared plus 1. And let's clean this up a little bit. Instead of saying negatives there, let's factor it out. So s plus 5. Okay, oops. There you go. So now what are we doing? So I see I have s minus 3, and so I know the Laplace transform of e to the at is equal to 1 over s minus a. So I'm looking at a is equal to 3, right? But now we have s plus 1 here, so we have the Laplace transform of negative t times, say, cosine of t, and that's going to give us s over s squared, s plus 1 squared plus 1. And taking a look at the Laplace transform of e to the minus t sine of t is equal to 1 over s plus 1 squared plus 1. Oh, and this one on the cosine should have had it shifted on top too. There we go. So I'm just pulling that straight from the table. You don't have to do it from memory. You'll have the table on the exam, and you're taking the exam at home anyway. How can I stop you? Anyway, so now let's take the inverse Laplace transform of, that guy. And what do we get? So we get 1 over 17 of times e to the 3t. This guy, we need to change the s plus 5 to, it's going to be s plus 1 plus 4. And then I'm going to get two pieces. So I'm going to get minus, coming from this minus sign here in the middle, e to the t cosine of t. And then I'm going to get another minus, just because, again, the minus sign, of 4 e to the t sine of t. And that's what we got. All right. So that's 4 problems from section 7.4. And so from here, you should have a good idea of how to get through it. Let's see. So let's jump into section 7.5. All right. So 7.5, let's start with number 1. Why not? So here we have y double prime minus 2y prime plus 5y is equal to 0. And they're telling us that y of 0 is equal to 2 and y prime of 0 is equal to 4. Now, most of these problems are going to be second order differential equations. So what we need to remember is that we have Laplace transform of y of t, and we'll call capital Y. Laplace transform of y prime of t is going to be s times y of s minus y naught. And the third thing we're going to use most often is the second derivative here, which is going to give me s squared times y of s minus s y of 0 minus y prime of 0. And these are the terms that we're going to be using most often. And before I run off with it, I am just double checking, make sure I wrote all of that right. Let me see. And I always get the two mixed up with the initial conditions, but it definitely looks like I wrote it right. Okay, good. So that's what we're running with. All right, so what we're going to do is we're going to go ahead and take this guy and take a Laplace transform using that. We're going to take this guy, take a Laplace transform using that, and then we're writing this guy as capital Y of s. The right-hand side is just 0. Laplace transform of 0 is, guess what? 0. So we don't need to worry about that. So this is what we get. We get s squared times capital Y of s minus s times y naught minus y prime naught, right? And we get minus 2 times s times y of s minus y naught. And then we get plus 5 times y of s is equal to 0. All right, now we have Laplace transformed our equation. We used this equation here to get this, and we used this equation here to get this, right? And so that's what you're going to do every single time. So it's something to get used to. Now we can plug in the initial values. So we get, say, we have s squared, capital Y of s, minus s times y naught. So that's going to be minus 2s, minus 4. Then we have minus 2 times sy of s minus 2. And we have plus 5 y of s here. Is equal to 0. Now let's group all the y's together and move everything that's not a y over to the other side. So we get s squared minus 2s plus 5, and this is times capital Y of s. And now everything that wasn't y, we have a 2s over here, plus 4, then we have a plus 4 again, and yeah, that's what we got. Okay, so now let's solve for, let's find our solution. So it's y of s is equal to 2s plus 8 divided by s squared minus 2s plus 5. And ta-da, we solved the problem, at least in the Laplace transform domain. So now the next step is to use inverse Laplace transform, which we just did 4 problems on. So we're going to take, so we have our y of s is equal to 2s plus 8 divided by s squared. Well, let's not just say s squared. Let's see. We're going to have s squared. Again, what did I say? So we're going to take this and we're going to put it in its irreducible form. So we have s minus 2s plus 1 is going to be squared. So we're going to have s minus 1 squared plus 4. Right, and that's what that gives you. Again, complete square, and that'll give it to you. So we have s minus 1 squared plus 4. All right, so again, what we're looking for is we have a Laplace transform of e to the t, say cosine of 2t, and so that's good, should give us s minus 1 over s minus 1 squared plus 4. Then we have a Laplace transform of e to the t sine of 2t, and that's going to give me s, not s, but 2 over s minus 1 squared plus 2. Right, so that's what we're looking for. All we need to do is add and subtract 1 in the s piece, so it's going to be s minus 1 plus 8 divided by s minus 1 squared plus 4, and distribute the 2. So now we have 2 times s minus 1 plus 10 divided by s minus 1 squared plus 4. All right, so that gives us 2 times s minus 1 on the top over s minus 1 squared plus 4. And then we have plus, say, 5 times 2 over s minus 1 squared plus 4. I know I'm skipping more steps now, but hopefully you're getting the idea. And now if I wanted to use the inverse Laplace transform to find, say, y of t, then that gives me, it's going to be 2 times e to the t cosine of 2t plus 5 sine e to the t sine of 2t. Okay, and that is the answer. Okay, so that's what we got. Not too bad. Okay, so that is the first problem we solved there. Let's see if we can find another one. Okay. Okay, so let's do number 5. So I have number 5, and what is this going to give me? So we have y double prime, or say w double prime plus w is equal to, say, t squared plus 2. Right? We have w of 0 is equal to 1, and we have w prime of 0 is equal to negative 1. All right, so Laplace transform both sides. All right, so remember, Laplace transform of w prime is s squared times big W of s minus s times w of 0 minus w prime of 0, right? So plugging that in, we get s squared times big W of s minus s times w0 minus w prime of 0. Then we have plus big W of 0, s, sorry, plus now Laplace transform of t squared, we know is 2 factorial over s cubed, we can use our table, plus 2 over s for the Laplace transform of the constant function 2, again, using our table. All right, plugging everything in, we have s squared here. Let me just write that clear. So we have s squared w of s minus s times w of 0, which is 1, plus 1 from w prime of 0, plus w of s is equal to 2 over s cubed, plus 2 over s. So we get s squared plus 1 on w of s, just isolating w of s, and moving everything else to the other side, we get 2 over s cubed plus 2 over s plus s minus 1. And so now to find a common denominator, that common denominator is going to be s cubed. So we get, say, 2 over s cubed plus 2s squared over s cubed plus s cubed over s of 4, sorry, over s cubed, and then minus s cubed over s cubed. And what do we get? So we get, say, s to the 4 minus s cubed plus 2s squared plus 2. All right, all over s cubed. Okay, now let's divide by s squared plus 1. So we get w of s is equal to s to the 4 minus s cubed plus 2s squared plus 2 divided by s cubed divided by s squared plus 1. Okay, now let's see what we got. Okay, I'm trying to find some way I can do some factoring here. Often when you have groups of 4, you can say look for a piece out of here and a piece out of here that sort of coincide that you can pull out. So what I was hoping is I can use the fact that we have a 2 here and a 2 here, and I can write this as s squared plus 1, and then I could pull out an s squared plus 1 out of that, but I can't. But what I can do is I can actually just split this into 2 pieces. So I have s to the 4 minus s cubed divided by s cubed times s squared plus 1. Now I can also write this as plus 2 times s squared plus 1 divided by s cubed times s squared plus 1. Now, what's nice is I can cancel this numerator with this denominator, and that just leaves me an s cubed, and I can factor out a cube here and cancel off this cube. So what does that give me? So it gives me an s minus 1 divided by an s squared plus 1 here, plus 2 over s 2 over s cubed. Now the 2 over s cubed corresponds exactly to the Laplace transform of t squared, because we have the Laplace transform of t to the n is n factorial over s to the n plus 1, and so the Laplace transform of t squared is 2 over s cubed. All right, so now we have an irreducible, but it's not even shifted, so we have Laplace transforms of sine and cosine directly, so sine of, say, t is actually 1 over s squared plus 1, and the Laplace transform of cosine of t is equal to s over s squared plus 1. So this gets even easier. So we get s over s squared plus 1, and we get minus 1 over s squared plus 1, we get plus 2 over s cubed, and so then changing from ws to little w of t, we get cosine of t minus sine of t plus t squared. Okay, cool. Piece cake. So this ended up being really easy to do. One thing that we could have done if we weren't using a Laplace transform is first we would find a particular solution for this equation where we had the non-homogeneous right-hand side. And what we would have guessed is we would have guessed, say, at squared plus bt plus c, and then we'd plug that into w double prime plus w and solve for a, b, and c, right? So that's what we would have done in the past. And then after that, you would find your homogeneous piece, which is w prime double prime plus w is equal to 0, which would have given us sines and cosines. And then we'd have to then write a particular solution plus c1 times y1t plus c2 y2t, where y1 and y2 are the solutions to the modulus equations, sine and cosine, then we'd have to solve for c1 and c2 using these initial conditions. That is rather involved. And here, in just a couple minutes, we got both our homogeneous solutions, cosine and sine, they appear there, and we already have the coefficients. We don't have to worry about that. And this would have been the particular solution we would have found. So, so in some sense, using the Laplace transform makes our life a lot easier. And so it's really nice. Let's see. Looking for one other problem that we could go ahead and try. All right, so I'm going to throw in an extra problem here, and I'm going to take a look at number 35. Now, on the exam, we're not really going to have enough time to solve these. So I'd say y double prime plus 3ty prime minus 6y is equal to 1. All right, and here we have y of 0 is equal to 0, and y prime of 0 is equal to 0. So this is a problem where we don't have constant coefficients, but I'd like you to be able to still do it. I don't want you to solve the whole problem. You can do that, but it'll take too long in the exam. What I want to see is you to change this to the equivalent differential equation on the Laplace transform side. And what's going to come down to this is, again, we have our Laplace transform of y double prime being s squared times y of s minus s times y of 0 minus y prime of 0. We know again also that we have Laplace transform of y prime, and that's going to give us s times y of s minus y of 0. But the thing is, we don't have y prime times a constant. We can't just pull a t out of the Laplace transform. So, but what we do know is if we take a Laplace transform of t times, say, some function f, then this is going to be minus d by ds of f of s. So that means that the Laplace transform of t times y prime is going to be the net minus the derivative of whatever this is. So it's going to be minus d by ds of s y of s minus this constant y of 0. And what is that going to give us? Well, it's going to be minus the derivative of s times y of s, which we can do with the product rule. So it's y of s minus plus s times y prime of s, and the constant derivative is 0. And so then we get minus y of s and minus s y prime of s. Okay, so what we're going to do is we're just going to go ahead and plug all these in, and then we'll get our differential equation. So, so what we're going to get here is we have s squared times y of s minus s y of 0 minus y prime of 0, and that is coming from this piece here. And then we're going to get plus 3 times ty prime, which we just said is minus y of s minus s y prime of s. Then we're going to get minus 6 times big Y of s is equal to 1. All right, now let's plug everything in. And so we're going to get, say, s squared times y of s. Our initial conditions are here, are all 0. So that's going to be 0 and 0 out of those guys, so it disappear. And so we're going to get, say, minus 3 y of s. Then we get minus 3 s y prime of s. Minus 6 y of s, and oh my goodness, I said the Laplace transform of 1 was 1, and that's certainly not true. It is 1 over s. So this should be equal to 1 over s. Okay, so just being organized, so then we see that we have minus 3 y prime of s is equal to, let's not say that, plus s squared minus 9 times y of s is equal to 1 over s, right? And so this is now a linear differential equation in big Y of s, or the Laplace transform. And where we have another condition now that we talked about last time, and we know that if we have a function of exponential order, then we expect y of s limit as s goes to infinity to be 0. So this is actually an assumption we're throwing in here. We don't know ahead of time that the solution y of t is going to be of exponential order, but we're really hoping it's going to be. Okay, so we actually kind of know just from this bit it should be, just because you should be getting things like sines, cosines, and e to the t's, something like that. But yeah, but for now, for us, we're just making this assumption, limit as s goes to infinity, y of s equals 0. Okay, so hopefully everything's clearer now, and we can feel ready for the exam 3. Again, this problem's like number 35. This is as far as I expect you to take it. I do not expect you to actually solve these problems just because it takes too long in the exam. And there's too many little spots to where you can actually end up screwing up. And I don't want to make a super tricky, extra long problem where you can just blow yourself up. So yeah, I just want to make sure you can do this step here. And so then that's what allows you to convert to a new differential equation. In any case, everything else we talked about. And yeah, good luck on the exam and good luck with your learning. All right, we'll go back to my office. Okay, so that's the problems from 7.4 and 7.5. Hopefully you found that informative and you feel more ready for the exam. So if you have more questions, again, ask them on campus. And other than that, good luck.